Okay, so this afternoon we have Professor Chong-Sun from National Tsinghua University to tell us about his proposal for a quantum mechanical model for black holes.
Thank you. We have excellent lectures already from many people about black hole. So I don't have to say too much about the problem of black hole. So maybe I start with my motivation. Let me get some pen. Oh, here. So for me, I started to get interest in black hole, of course, for a long time. I work in string theory. I have seen people counting microstate using supersymmetry. Of course, very interesting. But for me, still, when people talk about black hole in string theory, is something still quite far away from the black hole we have in nature, which is not supersymmetric. And also, the way to solve the puzzle usually rely on another thing, which I don't always understand. For example, the island proposal. I think Samir talked about that already. So actually, I start from recently. I start from thinking about the page curve and how I come to think of this model. So I will skip all the not logical steps how I arrive at the model. But one thing which worth mentioning is that I was always thinking about the atom. Of course, problem of atom. Atom has a discrete spectral line, right? This lambda, maybe sum over 1/2 square, n square. That kind of phenomena, which is not possible to explain in terms of classical E&M or classical model of atoms. So that's how Bohr come to explain this using a model based on stationary state, eigenstate, so existence of eigenstate. Right. Of course, then that kick off quantum mechanics, and then eventually quantum field theory, interaction of light with atom, everything come. Right. So I was thinking about, could we use black hole in some way like this? Of course, people talk about black hole as atom for a long time, like the hydrogen atom. But I'm really thinking about, in this setting, how we may use a black hole like an atom to learn something about the ingredient of quantum space itself. So black hole has a lot of puzzle. I mean, we heard about this already. Entropy, for example, the Bekenstein-Hawking entropy, this area law. Right, the existence of something like a thermal behavior, something like a temperature, Hawking temperature, which is so I will be talking about just ordinary non-supersymmetric black hole in four-dimensional space-time. Page curve, for example, chaos. So right, the problem is how to come up with some consistent way to explain all these phenomena, which came out from some effective field theory type of understanding. So we also learn a lot from this workshop that somehow you need something new. I mean, even over lunchtime, you say we need something new. So more to add on to the effective theory understanding. So what kind of new ingredient? I think there are two kinds of ingredients we can think about. Either you start from the original language, and then add some new thing, right? So this is original language. I mean something like maybe GR or QFT or effective theory, blah, 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 and then you add new effect, non-local effect or non-continuous geometry, yeah. But you can also change the language somehow, maybe. New observable, new language. It will be more like maybe like Bohr atomic model, something really cannot be faced in terms of the ordinary classical physics. So so my experience with string theory, one thing I really appreciate, enjoy much is about the emergence of space-time from matrix model. So BFSS matrix model, just to say more specifically. So probably everyone know about, well, I should not say everyone know about. If you're not old enough, you will not know about. So it's a maximal supersymmetric quantum mechanics. So it has some Lagrangian or action, yeah, some x dot square, right? Something like this, and then some fermion, and then some. It will be very schematic because I'm not going to use any of this. Yeah, so. Yeah, something like that. There's a trace, of course. There's a trace, and then there's some large n NTHU brane quantum mechanics, and then if you do large n, then it's supposed to give you a description of M theory in a sector of LIGO momentum with n, and then you can form a lot of bound state, and then provide some effective description of string theory. Suppose, yeah. So I think it's really beautiful that this model has one interesting thing is that this model has emergent space-time or emergent space. The model itself is just quantum mechanics of matrices. So these are matrices. Now the fermion itself, most of the time you don't really care, only the boson. Right? In the model, which I'm going to talk about later, the fermion play very essential role. So, but anyways, just for this model, you have all of this, but most of the time people only look at the boson. And I think it's interesting, but maybe not so much discussed. Okay, so the solution to this, the equation of motion. This is like this, right? A is from 1 to 9. So. These are the transverse coordinate of the D0 ring in this 10-dimensional space. Yeah. So the equation of motion, right, look like this, summing over A. So you can have a solution that this is 0, of course, right? Commuting background, and people talk about this, and then people do compactification of this kind of background, and then we cover so-called DP branes. So from D0 brane, you can actually recover this DP brane super young mu. So this is Watty-Taylor. Exactly when, 98 maybe, I don't remember. So by doing some images and then using the off-diagonal block element as an open string, we construct the Fourier mode, and then you can do this. There's another solution which is also very interesting. It's much more interesting. Is to consider this. This is called Moyal space. So this gives a non-commutative super young mu, and this is motivated by exactly that in dimension, you can compactify on non-commutative torus, and then you get, yeah, this kind of thing. So from the M theory. So it's quite interesting that you start from matrices, and then the matrices, you can think about them just like one particle, right? Let's say if they are moving in 2 dimensions, these are like a pawn moving in the space, and then these are the coordinates are labeled by the indices of the matrix. And then some collective system of this D0 brane, they form like a membrane or form a system that support a background of fluctuation, giving rise to some field theory. Right? This is the physical picture. So you have an emergent space or the time is there already, so you don't really need to imagine. But in the end, you get a space-time. Sometimes the background preserves Lorentz symmetry. Sometimes it has a reduction of Lorentz symmetry because of the existence of some parameter, right? But in any case, you get some interesting long-range, low-energy dynamics on this background, supported by on this background. So would that be possible that a black hole is like this, right? We need something new. So is it possible that the horizon, yeah.
So the right-hand side of the second equation, theta AB is
Constant.
so it means identity matrix.
It's just a constant, and then there's an identity here, yeah.
So if the X is a finite dimensional matrix,
Then you cannot do that.
then you cannot.
Yeah. Only for infinite dimensional. It's like quantum mechanics, you cannot have this if you are infinite dimensional. Yes. Thank you. Yeah, so you really need a large N to recover this kind of interpretation. So, okay, are there any other questions? Okay, so the question I was just posting is that, is it possible the black hole horizon is also some kind of emergent configuration of matrices, right? The nice thing about this kind of philosophy is that you don't really have a general covariance or general relativity there. We construct emergent, so somehow emergent, so not fundamental. So there's a lot of room you can actually change things, accommodate non-local effect, and yeah. But still, it's come from some fundamental Lagrangian, so everything is still under control, right? So you don't make arbitrary assumption. Suppose everything should be able to derive from some fundamental Lagrangian. Once you decided to work on this theory, then everything should follow, right? Black holes should follow, for example. Now, unfortunately, and at least for this purpose, nobody has ever been able to construct a black hole explicit emergent configuration from that BFSS quantum mechanics. All you can do at most is to get some system in which maybe the partition function of that system behave in some scaling way like a black hole. Yeah. So some equation of motion like a black hole, but you don't really get the feature. For example, you don't really get the mass of black hole and the radius obey the Schwarzschild metric relation. You don't really see that. Or if you have a more complicated, or the entropy, whether you can count entropy in terms of microstate in this, for example, you can imagine you have some emergent configuration like a black hole, and then the fluctuation. You count this fluctuation, then you count the microstate. You want to reproduce the entropy, right? So this has not been done, not so far in the BFSS. The problem is supersymmetry. When you have supersymmetry, then this Lagrangian is uniquely defined by supersymmetry. That is very nice when you don't have to think about anything. Somebody tell you top down, this is the theory, right? But the problem is, if this is the theory, then you have to work out the content, then it becomes suddenly you tie your hand. You don't have much freedom. So what I want to do is to get away from this restriction. I think the idea of using matrices is nice, but I don't have to. I mean, like phenomenology, you can do a lot of model and then build model. You kept the basic principle of matrices, but you don't have to tie to supersymmetric construction. So, so these are the data. Yeah.
But this model, if I put it at finite temperature.
Yeah.
If I put this as finite temperature, then there is a very precise agreement with not only leading supergravity, but also the subleading supergravity. Right? I mean,
You mean the partition function?
numerical, the Monte Carlo simulations of, but these are thermodynamic objects, basically, you have
to put the temperature.
partition function. Yeah,
right. So, there's a lot of discussion about, for example, try to understand temperature or thermalization, ADS black hole thermalization in matrix model, but you put temperature by hand. Right?
That's what I meant.
So, on the other hand, so what I want to do is that actually to also the existence of temperature. to start from a matrix model, I don't have to put temperature by hand. Somehow the relaxation effect of temperature would emerge from something. You cannot do it with a supersymmetric model. Now, to give you the answer is actually, if you don't have supersymmetry, then you can have a mass term, actually a tachyonic mass term. Very much like what you talked about yesterday. At the tip of the potential, you have a tachyonic potential. That is the key to get us the instability. Yeah, I will show you. Okay.
So what? No, very specifically, what people have done is to look at the finite temperature version of this model, and then you calculate. You start with this action, and Euclidean compactify T. Okay, so then you calculate all the partition function, and therefore entropy or whatever you. So that's your calculation. That's a numerical Monte Carlo calculation. And then what you do, you go to the supergravity side and start with a hypothesis that this should be a D0 brane black hole. So there you also know, just from leading supergravity, what the answer is. But I guess in these models, I don't know how people derive it, the leading order, maybe leading and next to leading order corrections to supergravity are also known. So you know a little bit better, the departures from regular supergravity, how the thermodynamic quantities should behave. And there is an incredibly precise agreement. This is the result of
so in the yeah.
The big collaboration.
In the D0 side, supergravity side, do you put a temperature also, or you just consider some vacuum solution?
Side, you just consider the D0 brane black hole background. Okay, but then you put in supergravity corrections to it as well.
Mm-hmm.
This is high temperature, not low temperature. No, low temperature.
Yeah.
But there's an expansion, so you can, at very high temperature, the leading supergravity is good, and then there's an expansion in some T2D 14 by 16 or something. We are at all.
Correction means stringy corrections. When you say they do next leading order, that means stringy corrections.
So wherever the corrections come from, I think specific R squared, term in the action. It might be stringy or it might be quantum. Okay. But the dependence on the temperature is a question.
Yeah, I don't know. So certainly.
Very weird, pretty non-trivial powers of temperature come there.
Yeah. So it's I'm not sure what it's beautiful. From what you said, it's beautiful. Yeah, but it's not. Yeah.
It's like a canonical ensemble understanding of what you are trying to do. Really have the states of the black hole. Tell you what the states of the black hole.
No, it doesn't really tell you the state. Yeah. So you also don't have the horizon. So I don't know what background you have for doing the D0 brane Monte Carlo. So
No, there's no horizon.
yeah. Okay. So I want to reproduce this feature, and then Hawking radiation. So and eventually I will come to the membrane paradigm. This part is a prediction now, I think, because this list I will explain in the first hour, and which I did the first two I did 2 years ago, and then this is in a paper this year, Hawking radiation, and then this is supposed I will after today, after integrating in your comments, I will put the paper today. But this is really big paper, so I will use the second hour to explain. Try to. Okay. So the model model is very simple. So I want to talk about a black hole in our space-time. So I will have 3x, xa only, right? So these are n by n matrix, traceless. So SUN symmetry. And I have some fermion also. I have 2 fermion side dagger. Right? These are also n by n. Now the model itself, the Lagrangian or the action. So you have x dot square, and then you have xx square, very similar. Now the new thing is that now I have a term which is a mass term, right? These are all positive. So in fact, this is a negative mass term. So there will be some instability. So we analyze the stability of the model next, right? And then there's a fermion kinetic term, and then there's a Yukawa coupling. So this psi are Mn, and then a alpha. Alpha is 1, 2, so 2 by 2. These are Pauli matrix, just Pauli matrix. But this is the model, basically. Then, yeah. Yeah, okay, good. So in the original paper, I didn't gauge it. So that is ungauged. So I can count the state. It's important that I can count the state without getting rid of those state. But actually, then I now understand you can actually make it gauge. So to fast forward the story, so the story will be, I have a black hole here. This will be described by this matrix model. Right? There's a black hole block. There's a black hole. So A. And then there's a block which I call environment also. And then there will be some off-diagonal block. These are like open string. These are like brain, and then you have environment, which is like a bigger brain, and then these are open string connecting them. Yeah. So the gauge symmetry should be imposed on the whole matrix. So there will be Gauss law on the whole matrix. And the Gauss law, if you look at the Gauss law, is something like this. If you only have the black hole, then you only have the charge of the black hole, like the charge on the horizon. So the black hole for me is the fuzzy sphere will be the horizon. So but if you look at the whole, actually there will be contribution from this link. There will be additional contribution from the W. So it's only in this sense that the Gauss law is constrained. And then later I will explain, once you impose the whole Gauss law, the charge on the horizon, this I call parton, that's why I call rho of P, become identified with the charge on to the environment, to the Maxwell field in the buck. In the sense, they really couple correctly to the divergence of E in the buck gauge field. So this rho appear there. So in that sense, it's become really observable to the Maxwell field outside. Yeah. So so to answer the question is gauge. But for the moment, let's forget about the Gauss laws first and analyze the model. Okay. So because I'm not doing supersymmetry, so there are lots of parameters here. All these coefficients are free in principle. So there's a time, so you can use a time to scale some of the parameter. So for example, you can use a time scaling of time and fix the parameter to be some form. So let me fix the form to be MP over n squared, right, in front of this term. So that I can scale it up to a Planck scale, some mass scale, which I call M Planck. And then for the purpose which I want to do later, I want to have an equation of motion which can give me some fuzzy sphere. So I will fix this relative coefficient to be like this. This is the model. Now, then the fermion term, I can scale the fermion. So I consider this normalization, canonical normalization. And then now I have 2 more terms, which I have 3 coefficients. So this term I will call it A2. I mean, it's not important here. I mean, but So just once and for all, right? Let's fix it. Yeah. To see the model. So A2 MP n square. Right? And then here you can, because of dimension, the whole thing is dimensionless. This is time, so you need some dimension here. So let's call it MP. So coefficient is not fixed, so you can actually put some coefficient here, which I put A0 square. So the model has two free parameter, A0 and A2. And it's like doing standard model. I mean, you have charge and hex coupling. These are free parameter. So let's do that and try to see what happened. So first, if you look at the background, background solution, so static and solution, so the equation of motion actually become this. So this is generalizing the BFSS, which equation become this. So, by the way, sorry, let me comment one more thing on this, on the model. So this is a negative mass term, which is very important. So we will comment on this stability, right? Also, and the physical effect of this. Stability, then we will look at the classical and the quantum. Both, yeah. This term is a bit funny. Oh, sorry, the side deck is missing. This term is a bit funny because it's not like the usual thing, which is a commutator, right? So in fact, when I first showed this to friends will tell me, friends can tell you honest thing, and they say, this is funny. I mean, this should not work because it's not like, where's the propagation? Because the commutator here is important to reconstruct some propagating degree of freedom in space-time, the commutator. This, because X become covariant derivative, and so you need, usually, that's the story, right? So here is a Yukawa coupling without commutator. So what's going on? Now it turns out this is really, I didn't know in the beginning when I first wrote on the model, right? But then later I understand better. So it's a bit of luck that this fermion actually doesn't move on the horizon. It can be identified with the picture is that I will show you. I mean, of course, there's a B field. There's a monopole B field on the fuzzy sphere, and then all these things are not propagating degree of freedom, but they are Landau level, lowest Landau level degree of freedom. They just move on circle, basically, quantized. Right? So in this sense, it's actually quite interesting. I will comment on this later. Okay. And this play a very important role to get to the membrane picture. Okay, so the equation of motion, the solution, you can have a E algebra type solution, right? Let me fix the location like this. So you can have a solution which is XA equal to JA, where JA obey the angular momentum algebra. Right, so you can have such a solution. Now, X is n by n. Now, this relation just tells you that actually X is a representation of SU2. So X is a representation of SU2. Now it's n by n, so it's a spin J representation, where J or n is 2J plus 1. So, I mean, you have the size of the matrix go from minus J to J, right? 2J plus 1. So this is the relation. The matrix model gives you an n that determines the spin J of the representation. So as a representation, of course, the chi-square is a constant. This is what Shamit talked about yesterday. This is just the chi-square. This is JJ plus 1. So that is n minus 1 over 2 times n plus 1 over 2. So this is what Sumit showed yesterday also, right? So you get this. So this is the size of the fuzzy sphere. Now this x is dimensionless. So let me introduce a dimensional coordinate y, which is related to x. To get rid of this 4, so let me multiply by 2, and then put a length scale, put L prime. Right. So eventually L prime and M prime are all related to the Newton constant G. By the moment, just put L prime. So then y square will be equal to R square. Sorry, R square. Yeah, R square, where R is n times L prime. So we get a fuzzy sphere. The size is proportional to n, and it's non-computing because of this representation, the algebra. Right? It's called fuzzy sphere because it's like a sphere with SO3 rotational symmetry. In some sense, if you take n go to infinity, then you recover the usual sphere. In the sense, if you have finite n, actually the algebra function on this fuzzy sphere is truncated because when you have n by n matrix, when you multiply enough time, you actually don't generate new function on the sphere. So that's a truncation of the spherical harmonics on the sphere. So in the old time, people call this so-called giant graviton. Right? It's big enough so it occupies the whole sphere. But if n go to infinity, you go to the smooth sphere. But for n finite, you can think this is like some discrete version of a sphere. Yeah, sorry.
As you take n large,
yeah,
does the right-hand side, this 2xb somehow become small?
You mean the commutation relation?
Yeah.
Now this is exactly satisfied, so nothing gets small here. But the commutation relation. Okay, so if you use a y, use a y, I think that become 2I L prime epsilon y, something like that. So
okay, I think I just got confused about something because the equation of motion required that double commutator to be 0.
Yeah.
But now it is not 0. So I was thinking it should become small in some way in this limit.
No. I substitute this XAXB. Or let's see it. Yeah. So if I substitute XAXB equal to I epsilon AB C XC.
No, I agree that is true.
Yeah.
I don't.
Okay.
It's just I don't understand the equation on your first blackboard where you showed that the equation of motion requires that commutator to be 0.
Okay. So this is just some old model, BFS physics model, which has nothing to do with my model.
So that's that.
Yeah. So I'm just motivating that this model is nice, but it's a flat direction, only flat direction because of supersymmetry. So you cannot, it's hard to get some compact object. Yeah. Okay. The fuzzy sphere itself, which there's a construction which is useful for me later. It's the coherent state. I think it's very familiar to people in condensed matter physics also. Coherent state construction. So you want to physically construct a Hilbert space representing this. Instead of using the usual discrete, of course, it's a representation, so you can use JM, right? This angular momentum basis, right? That's you can use this discrete basis, but instead of using this, you can do some kind of like a Fourier transform to get to some continuous representation, which is called coherent state. So basically, instead of using J and M, some discrete label, you want to use the angular coordinate on the sphere. So let's say phi. So phi at the theta and phi, angular coordinate on the sphere. So any point on the sphere, here, let's say here, omega, right? Unit sphere can be obtained from this point, the North Pole, by a rotation, right? Some rotation. So you define a state. So you start from the highest weight state at the north pole, and then add on this. This is a SU2 group element. So something like I theta, maybe JY, and then I phi, JC, that kind of thing. I don't remember the formula, but there's a formula. I mean, there's a Lie algebra. This is the usual how do you call it? Tangent space, right? Tangent space of the Lie algebra. So you can do that. You can get this state omega, and then you can define a so any function or any function on fuzzy sphere. So any operator on fuzzy sphere S2 n. I can consider this and define something called a symbol, which has become a function on the fuzzy sphere, a function of angles, right? So the purpose of doing this is just because then we can really see how the non-continuous geometry come about. So if you have this, right? So this is not the same as the product of the two functions, because there's a longitudinal operator product here. So in fact, what you do is that you define a star product, right? So there's a star product between them, and the star product right, and then there is 1 over J. In that case, the J is like controlling the non-commutativity here. I over J, I think. There's a derivative of A of F, derivative of B on G, and maybe it's not very important. I mean, there's some structure here, and then you see some kind of formula like that. So let me don't elaborate. But important thing is that you can see the fuzzy sphere become. You can study the fuzzy sphere just like you study any non-commutative geometry with a star product. So okay. Okay. That's now something quite important. So when we define this state, actually it's not unique, because although you can have a rotation to go from here to here, but you can always you can do an arbitrary rotation, right? You can always do arbitrary rotation, I alpha and then J free there. It will do nothing to the state, because it's there. You rotate anything, it doesn't, right? So when you do this here, then you pick up a term. So if you change your G to be a G multiplied by this additional factor, your state will become, you pick up a term like this. Yeah. So there's a phase ambiguity in the definition of phi. Now, as usual, when you have a phase ambiguity, this angle can actually be local also. Depending on this omega, you can pick an arbitrary function here, right? So this is a local phase ambiguity. When you have a local phase ambiguity, that means you can define a Berry connection. So you have a Berry connection there. So if you now go through the calculation and try to get what this Berry connection is, and this Berry connection, in fact, is a monopole. So the monopole has a Chern number. The Chern number depends on the representation, the size of the representation. So the monopole, in fact, look like this. J So this is the monopole. Just want to make sure the normalization. Yeah. D is a D. Yeah, D is the That's correct. D is the derivative on the sphere. So you can say this is like the if these are local coordinate on the sphere, something like that. So theta and phi direction. These are theta and phi, for example. Then you can. There's no matrices anymore because I was going from the discrete basis and now go to this continuous representation, this oriented state, and then we discover that there's this phase ambiguity, so we can naturally define such a monopole. Yeah.
But I mean, typically, what appears as a derivative in the continuum appears like a commutator. In terms of the matrices. Is this the same kind of thing or like?
Okay. That it's not a commutator. I don't know what you mean. You mean there's a field strength, and then for example, there you can have a field commutator of X, give you a field strength, and then you for the field strength, and you see there's a monopole. Yeah, but it's different here. Also, but it's this monopole is actually, okay, to explain why this is different. One reason why it's different is that this monopole actually is visible only to this fermion. It's not visible to the X. This is like because X has a adjoint matrices. These two indices, this U1 transformation will cancel for this X, so we will not see. But for the fermion, this is the funny thing. I mean, the fermion actually, although I wrote as a matrices, right? So it's like this M, N, K, Heidegger, K, M, right? Although I wrote like this trace as a matrix, these are matrices, but actually this fermion, only these indices is coupled to X, the second indices. The second indices is like a flavor indices. So we should not think of that as a adjoint matrices like a BFSS, but it's an n favor of fundamental fermion, and this fermion will be sensitive to this. Yeah. So it will couple. It will couple to this fermion, to this monopole. So, but here you can still see why this is monopole because, for example, if you compute the field strength, dA, then you get J psi theta d theta d phi. So you integrate over the sphere and 2 pi, then you get J. Right, so let's say J over 2 pi, and then psi theta d theta d phi. So this is 0 to pi, 0 to 2 pi. Right, this is 0 to pi. So here you get 4 pi. Yeah. 4 pi or 2 pi? 4 pi. So you get 2j. Okay, 2j. So maybe I'm just a bit confused. Maybe it's okay. 2j is n minus 1. Okay, yeah, that's correct. Yeah. So let's continue with the explanation of the model. So you have a solution now. So we can ask what's the energy of this solution. So then you just substitute the fuzzy sphere background. So you have the Hamiltonian, right? You have the energy, the bosonic part. You have mp over n squared, and then x squared plus 2x squared, and then they trace. Okay. So now xx squared, then you get minus, you have I epsilon a, b, c, x, c, and then I epsilon a, b, d, x, d. So you get minus 2x squared. This is 4, sorry, this is 4. Okay. So you get 2x squared, then you get 2mp n squared, and then trace x squared. Now x squared, we said already, this is n squared minus 1 over 4. All right, so forget about the n. So we were doing n very large, right? So forget about the 1. So that's this. So this gives you mp over 2, and then trace of 1. So this is n. And I somehow missed the minus sign here. It should be minus. In the action is plus, so this is minus. Yeah, so it's minus. Okay, so I get this energy from the boson. Now, what about the fermion? The fermion, what you need to do now is to quantize the fermion in this fuzzy sphere background. So quantize. Fuzzy sphere background. Oh, I only have 15 minutes before 2:30. I should be fast. So what it means is that you have the condensation is trivial. I mean, the condensation you look at the kinetic term, right? So the kinetic term use same condensation. You get the momentum and the coordinate, and then you get half fermionic oscillator. Okay, get fermionic oscillator from here condensation. So some psi dagger psi equal to 1. Yeah, put the matrices indices appropriately. So then you have this potential term, A2 mp n squared trace of, right? So it turns out you can, it's very, very simple. You can diagonalize this. You can diagonalize this just like you do Dirac. I mean, you say you have some U and D dagger. Then, of course, then you can, in this fuzzy sphere, you substitute the background, and then you change the you do some eigenbasis transformation, and then you can diagonalize it. So this is you have something you have to multiply to do the eigenbasis transformation. You do all this, then in the end, this operator is diagonal. I say eigenvalue of n over 2. I show you later, but just the result. Then you have U dagger U. This is MK U MK, and then plus D MK stuff like that, and some over M and K, all of them from 1 to N, right? So you have 2N, you have N square of this, and N square of this. Now this is very simple because this is This is typically like angular momentum algebra. X is the angular momentum, right? And then this same over 2 S is also angular momentum. So in fact, you have a problem like this, S dot J here. So you can do the usual thing. I mean, then you can diagonalize. Very simple. Okay. So in the end, you get this eigenvalue structure. So I will skip this part. Right? So what happened is that you have psi, m, and alpha. So you have 2n squared of this guy to start with. Alpha is 1, 2, so you somehow put half of them called U, half of them called D. Each of them are n squared. So you have this here. So now you have a Fermi C problem. It's a huge degeneracy. All of them have the same energy, just one ground state energy, n over 2. You just have to decide whether you excite that energy or not, right? So if you excite all the n squared, then you get 2n squared times this. Or you can decide to see in the lower bottom, then you have no excitation at all. So in general, you have a Fermi C, in which this, if I call this the number of U get excited R, and the number of D get excited S, right? So the energy from fermion is just equal to A2MP over 2N. So I combine this N over 2N square already. So R plus S. So R is the number of U get excited, and S is the number of D get excited. R plus S is from 0 up to 2N squared. So you can also look at the degeneracy of a general. So let's call it N. A general configuration of RS, the degeneracy, not degeneracy, the number of microstate with that with satisfying this condition is this. Right, that's the degeneracy. Suppose I look at the one with in the middle. So this is called the half Fermi C. So we get some energy, which is proportional to n also now. So combined with that, then you get some energy, which is proportional to n. Okay. Suppose you do that, then you look at not just that. Okay, not just that. You do that, but also one thing. We notice that psi. This is a symmetry. It's a continuous global symmetry, right? So you can see in the model. Yeah. So then there's a letter charge. So the R and S actually, R minus S is a letter charge. It's a constant. So this is very much like Dirac fermion. Number of electron, positron, the total charge is a constant, right? So it's charge conservation. Later, in fact, we will see that the U and D carry charge exactly like electric charge. So this is really an electric charge up to a charge of each individual fermion. So we can consider an ensemble of state in which this is half Fermi C, and then with R and S equal to constant. So let me say n squared over 2, for example, just the reference point. One is plus n, the other one is like this. Then now for example, for n equal to 0, you can have some state, and for n equal to 0, you have some. So this is a function of n, right? Now, turns out this function, of course, is trivial. I mean, you can see that it's maximum at n equal to 0, and then so it's the maximal degeneracy at n equal to 0 in that, and then like this in a large n, some Stirling formula. Very easy to do. Okay, so there's a ground state degeneracy, which is 2n squared. So now if you plug back our relation, radius is NLP. So this is 2R square over LP square. So it can be made R square over pi R square over G, right? So the Hawking, Bekenstein-Hawking entropy formula, if G is pi over 2 LP square. So this determines LP in terms of G, right? Energy, sorry, any question? Okay, the energy for this configuration, the fermion, I substitute back here, here, right? So I get A2 over 2 MPN. So together, the total energy will be MPN over 2 A2 minus 1. A2 minus 1, yes. So, so I want to identify this, right, with R over 2G. Now R is NL Planck over 2G. So the N matched already. So this relation can give you M Planck in terms of G. Okay, just some relation which are like a square of G or something like that. But so in the end, we produce the Schwarzschild mass radius relation and also the entropy. Now, the reason why we consider this is because this sets, actually, if you look at the Bekenstein entropy bar, something like S 2 pi, this kind of entropy bar is saturated for this configuration, but otherwise the inequality is satisfied. So the black hole saturate this inequality is known also in the past. So that's why we consider this particular configuration. So half MEC, right? With for n not equal to 0, this is something like we'll see later. Q is proportional to R minus S. So that will be the charge of the black hole. Let me pause for a second. Are there any questions about this part? Yeah.
Can you explain again what are the free parameters in your theory?
So far I have not fixed any parameter. Okay. So I have the parameter A0, which is over the x dot square, right, to A naught square M pen. And then there's a Yukawa coupling with a A2. So there's a Yukawa coupling. N square, sorry. So these are the two parameters, which hasn't been fixed. Yeah. Yeah. So at least I want A2 to be greater than 1. Yeah, only that. A2 greater than 1. Yeah. Okay.
Just so they understand.
Yeah.
So this is the ground state has 0 energy.
No, it's not supersymmetric. No supersymmetry. If I have supersymmetry, I would not have this fermion. It's not in the same representation. Yeah. Also, I will not have the mass term. Yeah.
So this is the ground state. This degeneracy is for the ground state for 2n square.
Not for the ground state. For this state with a half MEC field. So with excitation. So you can imagine this is like a fuzzy sphere with excitation. With with this thing here, and this is the microstate we are counting.
Oh, I see. So that has this energy and that has the entropy, and so therefore it will have a temperature.
The temperature will come later. It's not so clear, right? I mean, it's a quantum space. Why does it have a temperature? So the temperature, I can explain now. Yeah. So yeah.
Entropy
No, then you get 0. I think this GR, right? This relation obeys GR relation. So it has to come from some dynamics of the model itself. It's not just the extensive variable relation. Yeah.
Del S, del E is 0? Or
There's no temperature. Classical space-time, you don't have a. I don't have horizon also. I mean, no, I don't have metric here.
No, I'm just saying
Yeah.
that as a system,
Yeah.
some given energy
Mm-hmm.
and some given degeneracy,
Mm-hmm.
right? So usually I can approximate that system by a canonical ensemble with the temperature given by del E, del S. So that's not that here. You see what I mean?
I see what you mean. Yeah. Yeah, I thought about that. But that's assuming the energy. That's with the energy. Is it with the energy constant? That's a relation.
No, what I mean, you have an E which is I'm a little bit confused.
E is proportional to n.
E is proportional to n.
Yeah.
And S is proportional to n squared.
Yeah.
So S is like E squared.
So you are talking about this relation, right? 1 over t is ds dE. Right. So let's say S. I mean this is a usual Hawking. I'm just having the usual Hawking relation. Right. 2g. So so E is R, right? So I can have 2g ds dr, and then this is 1 over 2, and then dA square dr.
Yeah, that's exactly what I meant.
Yeah. Okay. So let's see. A and then dA. A is 4 pi r squared. So a pi r. Yeah. So I think this is right.
Yeah, that's correct.
Yeah. So you get something maybe like r cube. Is it right?
No. Should be 4 pi.
I know. It should be 1 over 4 pi r, right? So some.
Never mind. This S and this E give that T.
Yeah, give some t. Yeah, but it's not. I don't know the meaning of that t.
No, that I understand.
Yeah, it's not a statistical mechanical system. So maybe we yeah.
So can I ask?
Yeah.
So suppose we consider other classical background which satisfies the equation of motion, and then we consider quantum tunneling between the classical vacuum. Does that lift some of the vacuum degeneracy?
If there's a barrier between them, then yes, there's a tunneling. Now, here, there's no potential, no barrier between them. These are just degenerate. But there will be another tunneling, which I would be talking about. Yeah. But we will come later. So I have to rush, I think. So let me just make a comment. All this can be done for Kerr black hole, right? For rotating black hole. So the Kerr black hole has a similar relation with energy, momentum, and entropy, more complicated. But you can reproduce those similar argument with a rotating fuzzy sphere. So you spin the fuzzy sphere with angular velocity along the z-axis, and it become toroidal ellipsoid, and then that reproduce the elliptical horizon of the Kerr black hole, and also the angular momentum of this spinning fuzzy sphere. If you match with the angular momentum of the Kerr black hole, that actually gives you a condition. This has to be power free. So this is important. This will be used later. So this is the first constraint in the model. Otherwise, there's no other constraint of the model. One more comment before we take a break about the stability. right? I mean, you should be worried about the fact that we have a negative mass term in the model. So negative mass term means there's some instability in the model. So if you have if you look at this is V, it's like this. So roughly speaking, it's like this, -4, yeah. So this one is anti-emission, right? So this is positive, this is negative. So it's like Higgs potential. So if you look at the abelian background, this is very bad. But now let's say I look at the fuzzy sphere and look at the fluctuation of the fuzzy sphere and try to see what kind of instability you have, then it's not too bad. So you analyze the fluctuation. Like that, right? So and then you find the potential can be written in some quadratic form, right? With a kinetic operator here, which the form is long. I mean, it's just some angular momentum and something, and then acting on that. So it can be diagonalized. Again, using angular momentum algebra, not difficult. So you find that at 1 mole only, 1 mole. So these are the eigenvalue problem. 1 mole with lambda negative. Actually, equal to minus 2. It's not too bad. But anyway, there's a negative direction. So what this mole does is this mole is correspond to J equal to 2, L equal to 1. I think so. Let me. Yeah, so this N here actually is constructed in terms of some angular momentum. So this epsilon A is a matrix. Is this matrix? It's a spin 1. So this act on the vector indices of the fluctuation. Yeah, and then there's a angular momentum. This is the usual matrix degree of freedom. So it's some kind of spherical harmonics construction, vector spherical harmonics. So you have to, this is the usual harmonics, and then you have the vector apart. Yeah. So yeah, okay, maybe I think I skipped this analysis. It's in the paper. But there's one thing which I didn't, it's new, which I haven't talked about this in the paper, is this mole, if you look at it carefully, then you find that actually it does condense. I mean, with this mole, you find the potential. It does have a, so it's unstable at origin, and then it condenses somewhere, right? So, okay, that's good. First, it's not run away. It's some nice behavior, but still it's not good, because if you have fuzzy sphere, you have this, then this is more stable. So what happened to your fuzzy sphere? It will go to that configuration in some finite time, so it's not good. So, but then you look at the quantum fluctuation around this background. You sum over this, the 0 mole, yeah, sum over the 0 mole depending on the fluctuation, right? Then you can do that, and then you find that there's a quantum potential actually stabilize the whole thing, right? So that's good. So I will skip this part because of time. So let me just very quickly talk about the tunneling, Hawking radiation, because we just talked about this. So quantum mechanically, what we have is a vacuum. So you have a fuzzy sphere vacuum here, and you have another one here. let's say n pi. Energy is proportional, this is energy. Energy is proportional to n. So if this n times less than n, this one has lower energy. Now classically, these configurations are stable, but quantum mechanically, this thing can tunnel. So, so it's very much like black hole now. Black hole is classical, is stable. Quantum mechanically, black hole can decay with a tunneling rate. The black hole tunneling rate is something like defined to be minus dm dt 1 over m, right? So it's some q over g square m cube, something like that. So in our language, I want to get a 1 over n cube, right? If you really want to say this process is describing Hawking radiation, then at least the rate has to be right? The first thing is the tunneling rate from this quantum mechanical process should reproduce this. And also I should somehow get the temperature, right? Temperature. So the rate. And do I see a temperature from this? Temperature means if I look at the probability distribution of individual energy momentum, angular momentum packet, do I see this Boltzmann distribution, for example? Now, the time when you start looking at tunneling, then you see that it should not work because there are two problems. The first problem is that this is a very high dimensional quantum mechanics. So high dimension that you cannot really find the path. If you one dimension, there's only one way you can find the path, bouncing path, right? But in so high dimension, n is 10 to 50 or something, let's say for a black hole. So how can you find the path? It's very difficult. Unless you have some symmetry, like in quantum field theory, you have use symmetry, SO4 bounds or that kind of, yeah. But here, there's no obvious symmetry. So technically, it sounds impossible, hopeless to find this tunneling process. Another more important problem is actually this fuzzy sphere has a Fermi sea. So it has a Fermi sea. The Fermi sea has a size. Here you say you have n square state, and it has n prime square Fermi state, and these are different. Now, the Hamiltonian actually conserve Fermi number. So how can you go from a state go to a different state with a different Fermi number? So the amplitude, the overlap will be 0. So if you have, let's say, fermion n prime square and then x n prime, right? You try to compute over a long time and then try to see the overlap with from an initial configuration of fuzzy sphere and a n square of Fermi sea. This should be 0. 0. Now this is usually in path integral is computed in terms of a path integral, something like that. So you have a bosonic action, which you go to settle point. That is called a bounce, right? Suppose you find a bounce, right? And then you have the fluctuation, and you integrate over fluctuation. So that's the bosonic part. So you integrate over fluctuation. And then you have the fermion part. So you have some dt and then sigma a x a, the bounce part, and then psi, something like that. So if the initial and final state have different fermion, then this path integral will, then you have to integrate from different fermion, and this, because it's, as I said, this conserves fermion number, so it will not work. Now, the interesting thing is that this one can have 0 mole. If you have 0 mole, so that means, that means a mole which satisfies the equation here, 0 mole. So there will be, this will factor into some non-zero mole and then some 0 mole. So you have some additional Fermi oscillator now. So this oscillator can then saturate this and make it work. So how many zero mode do we need? So the difference in Fermi C, size of Fermi C is n squared minus n prime squared. If I say n prime is n minus n, so it decreased by the rank of the fuzzy sphere by little n. So this is 2n in the large n limit. So you need this number of zero mode. Now there's a favor indices. This is like this n is counting the favor indices, and then this 2 is counting the alpha 1, 2. So basically n zero mode, right? So can we find n zero mode from this here? So that depends on the bouncing property of this bouncing path now. So the claim is that when this is a monopole of C1 equal to n, this is exactly the number of zero mode that give you this factor and then saturate the Fermi C and then allow for a non-zero transition. This part is quite interesting. Good. So the first this tunneling process is basically like you have a fuzzy sphere n, rank n, and then nucleate a monopole. A part of it become a monopole, and then escape, and then become an n prime, smaller fuzzy sphere. And this is the Hawking radiation. Hawking radiation together with so what escape here is part of the space, quantum space, together with some of the fermion, some zero mode escape. So this is a space-time picture of what happened to the Hawking radiation in this picture. So these are not the quantum field theory degree of freedom. I'm not talking about Hawking radiation of a quantum field of neutrino or whatever. These are really the quantum space itself. The quantum space itself can radiate by this tunneling process. So the rest is just compute this thing, right? So it's a lot of very interesting story. So it worked. So in the end, we produce one of the Hawking rays. Yeah, this n cube. So we can talk more about this, but I think it will be too much technical details here. I'd also understanding why this is giving zero mode is interesting. And what do I mean by monopole? Okay, maybe I talk about this. This is the last thing I will talk about. What do I mean by this bounce is a monopole? So this is something which you suppose you define this A, you just define it to be XA n minus XA n prime, or this is n minus n, right? Define this matrix, and then you can compute the matrix element using the coherent state, and then what you find is that this indeed give you monopole connection in the large n limit. So so the bouncing path is actually like this. So the bouncing path will be, I start from XA n, and then minus a parameter, and then this AN AAA. So when gamma equal to 0, I start from this point. And then when you go on the gamma space, so gamma can be a function of time, tunneling time. So, and it will become XA n prime when gamma equal to 1, when you reach the endpoint. So this is a very nice, clear way you can write the tunneling path. And then using this, then you can now do the computation, computing the potential. So the potential, you have x commutator square, x square, right? So you substitute, this is like a perturbation part, and then this is a, so you get gamma square, trace a square, gamma cube, trace a cube, gamma 4, trace a well, roughly speaking, like this structure. Okay, so there will be some x and x there, but when you have a gamma cube, you have an expression you have to trace with VA, roughly speaking. So when we compute the bounds, right, the tunneling rate has two factors, which is the determinant of the fluctuation and the bounds. One of the things which we were confused, I'm confused, not we, only me, confused in the beginning is, how can we get a polynomial 1/n cube if you have something like that? If this v or this s here has this dependence, then naive guess is that all this thing will be like 1/n, n to some power, right? Then this will be some e to something 1/n, right? Either 1/n or n, I don't know, but polynomial. So you can never get you 1/n like this, because it's exponential. Now what happens is that this is really quite remarkable for this monopole. This matrix element here, in fact, is n not n. That's a lot. So that's how you can reconstruct this 1/n cube. But it's technical, but it's quite non-trivial, which I mean, it's not a coincidence that work, because these are not just fitting 1 and 2, because it's a whole dependence log come out, and so it's hinge on this monopole. Now this just one last remark. This monopole, when I wrote the paper in March, this is quite beautiful, but then I didn't ask a question, but then I asked a question later, then I realized this is an important question, which is monopole charge is a conserved quantity. How can you create monopole charge? If you don't have something already there, how can you create monopole charge, right? So how can you create monopole charge? This monopole has a Chern number n. So let's come back to the original construction. Actually, we have a monopole already in the Berry monopole. And that's the origin of all these things. So the Berry monopole is there. It's a big monopole. Part of it go out and then reduce to a smaller Berry monopole. It's still big. And so the whole story is consistent. Okay. So I think I will stop here. And the next part, I will talk about the membrane. We can have a few minutes break. Are there any comments or questions? Yeah.
This extrapolation of gamma from 0 to 1.
Yeah.
This path, is this an instanton in Euclidean time?
Yeah.
Oh.
Yeah. Because whenever you're tunneling, you have to go through classically forbidden region, right? Yeah. In that sense, it's instanton, but it's a monopole. Yeah. Yes.
In your model, you consider the quantum mechanical case, and you consider with the Yukawa orientation and also some kinetic term for boson field. But why do we need to consider the quantum mechanical case? For example, 1+1 and 3+1.
Mm-hmm.
Could we see any difference?
You mean field theory, or what?
No, just here for your model, and I just consider DT.
Yeah.
1+1 and the 3+1 case, and it's still UV complete for here. So, but if we just consider classical analysis and the low energy ground state, maybe no difference.
What do you mean by 3+1? You mean Yang-Mills theory?
No, not just Yang-Mills here. Same intention.
So what is 3+1 here?
3+1 because it just consider Yukawa, so it's still renormalizable.
I don't understand what you mean by 1+1, 3+1.
3+1 means
phi mean what?
I mean that your integration dt becomes a 3 spatial part and a 1 dt part.
What that mean the field theory?
But I don't know what is the meaning for t now here. If I want to see the emergence.
Well, you suffer with x, with free integration of x, then you don't have...
Yeah, then I have now. For each x, I have the 3+1 variables. 3 S1, S2, S3, and the t.
Yeah, so you have a space already. That's a field theory.
I don't know whether it's a space. If I have an emergence there.
Maybe you can show me later. Yeah, I don't understand what. Yeah.
Shall I understand xn and xn prime different classical solutions of the same theory, or do they belong to different theories?
No, same classical solution of the same theory, of course.
The same theory.
Otherwise, how can they tunnel?
Okay.
Yeah.
All right. Okay. And another question is, why do you assume the number of flavor is equal to the number of color?
Oh, no. It just happened here, yeah. But you can change the model. You can change NF to rectangular matrix. I don't know. I haven't.
And then the black hole will not be an interpretation, or?
You have one more parameter to play with. Maybe you can do something else. I don't know. I haven't thought about that yet.
So just so see if I understand your potential. So you have how many matrices?
3 matrices, 3x and 2 psi. Yeah, one
3x
complex
and 2
psi.
Okay.
Yeah.
And so you've got a commutator squared interaction amongst the x's.
Yeah.
And then the trace x squared is upside down oscillator?
Yeah, inverted harmonic oscillator.
Okay. So there's an unstable direction where the eigenvalues of the matrices can run away.
I think you just went off for restroom.
Yeah.
So we can look at the small fluctuation analysis. At the quadratic level, you have some structure like this with some operator, and we want to diagonalize that to find eigenvalue. So that can be worked out in terms of some angular momentum algebra. So in the end, there's only one mode which is unstable, negative, and that is something with a described in terms of vector spherical harmonics is something like that. So so this mode one can work out the potential fully, and it will be something like that. So that there's a condensation somewhere. But quantum mechanically, one sum over also the frequency, the ground state frequency, created by this mode, and then you find that actually the potential is stable. So there's a stability created by the quantum oscillation.
Okay.
Yeah. This is of order n, and this is order n square something.
Okay.
Yeah.
So ultimately, the ground state there's a ground state.
Yeah.
Okay.
But doesn't mean this term has no effect still. This has an effect, for example, later when you talk about the off-diagonal, this link, this thing does condense in that case. And that is the thing when you condense, it connect these two blocks, which I want to talk about next part. Okay. Okay, so let's have a break now. Yeah. So far, you can look at this model, and then you can try to. That's what we did. I mean, we tried to check with known property of quantum black hole, try to reproduce them. Right. So far, it's working fine. So then next thing to do is why not try to make some prediction, right? If there are any prediction we can make with this model, then you can test this model, test quantum black hole, and then test quantum gravity. One thing is that this model, so far I have not seen long-range gravity, but there's a way you can see long-range gravity. I will indicate that later, right? One way to try to make a prediction is a membrane paradigm. Because the membrane paradigm is basically you try to send something to the black hole, and then try to see what happened, right? So it's a perfect place you can try to probe a black hole. In the membrane paradigm, you replace a black hole itself. You forget about black hole. You replace it by some fictitious membrane at a location. At a location delta. Delta is some Planck scale, L Planck to L Planck, doesn't really matter. So you impose boundary condition there so that we produce what the EM wave will do, right? We produce what the EM wave will do. So the statement is that if you put a current, electric current, so A denote the tangential indices on the, Yes, sure.
So if your quantum effects are generating some positive mass term for these matrices, so in what sense are you radiating things by your tunneling calculation?
Oh, I'm talking the tunneling. So it's
tunneling to where? Because if you've got an x squared potential, all the matrix eigenvalues are still, pushed towards the origin.
So
so where are these things radiating to?
So there's a different fuzzy sphere. So there's a fuzzy sphere, and there's another fuzzy sphere. So somewhere up, maybe they I don't know what happened, but I mean locally they are very, very sharp. But there's a fuzzy sphere here. They're not degenerate. So this n prime with a rank which is less, energy is smaller. So in this can tunnel.
So they're both centered at around x equals 0. Is that the idea?
No. So this one will be xn satisfy the algebra, and then xn square equal to some n.
So two different radius spheres.
Yeah, two different radius. Yeah, right.
Okay.
So it's maybe center at the same place you can. But actually, it doesn't really matter. I don't talk about the translation part here. So.
Well, they have to be centered at the same place.
Same. Okay, yeah, because momentum conservation, of course. So they collapse to this is the process I'm talking about.
Okay.
Yeah. So this can happen because of some monopole creation. This is the process. Okay. So the membrane paradigm, the statement is that if you have put a current, right, the current is proportional to if you put an electric field. If you put a tangential electric field on this membrane, it will produce a current, electric current. So this 1/4 pi is a conductivity. So ohmic current with a conductivity sigma 1/4 pi. So let me call this XX, right? Because here later we will have XY, which is a Hall conductivity. One thing important is that this current actually is a frame in the so-called FIDO frame. So what FIDO? Let me see. Fastidious, what? Who anyone remember? Remember FIDO? I have to look it up, but so I mean, there's a lot of different frame here, but this is a frame actually anchor on the membrane. If you look at the space-time metric, this is space-time metric. So at the location of this stretch horizon, right? Then you have this time factor. So this is the time factor on the stretch horizon, and then you call this a d tau square. So this is the frame this FIDO person will use. So this is basically the main thing. So this electric field, for example, electric field is F A tau. So or F A T if I lose a Schwarzschild time, and then with a F here, I think, yeah. Is it like that? Oh no, the tau is downstairs, right? So it's like this, yeah. So with the F downstairs. So this is this type of statement. This JA is a current which you put in the total action of space. So you have a Maxwell action, 4 dimension. So this is in the space. You have 16 pi. So this is in some Gauss unit. So in the Gauss unit, you have this 4 pi. Okay, this is related. But we use the Gauss unit, so it's standard unit. And then you add a term which is J, A, and then A on this horizon, So when you do the boundary value problem, not boundary, you do the variation, you get a boundary term here, got equated to this one. So JA, this JA, in fact is 1 over 4 pi. 4 pi because of the 16 pi, F, A, mu, and mu, right? So the membrane current relation, in fact, is a relation between the well volume electric field and the bulk electric field at the boundary, right? So this is a relation. So what that relation does is the following. So you have F, A, mu, and mu equal to E, A. And I said this one is equal to F, A, T 1 over F. Now, the normal vector to the horizon here is a unit normal vector. So N mu, N nu, G mu nu has to be equal to 1. So this is in the radial direction because it's normal. So N mu, in fact, is 0 time, and then you have a space. This is F 0, 0. So this is R component, and R. Yeah, this is, or you can say, this is F delta mu R. Okay, this is better to say, more clear. So the relation actually tells you F, A, R, and then F. You have square root of F, so F equal to F, A, T. So this is the A, T. Suppose you do temporal gauge, you don't have this, and then you have minus the T, A. And this FAR is just F, and then the AR minus the RAA. Suppose you do S wave, so you also don't have this. So in the end, you get a condition which is dt AA, dt minus F, the RAA equal to 0. Now this is nothing but just the ingoing boundary condition for A, because this, you can construct this tortoise coordinate, right? So this is in fact just dt minus dr star. So what that means is that A is a function of this, but not the other component. So this is ingoing. So this is just a statement of an ingoing boundary condition of black hole. So if you modify this relation, let's say instead of JA is equal to this, JA is always given by this, right? You have this. If you add, instead of just an ohmic component, you have some, let's say, Hall component, right? Then it will change the condition. So you may have something new observable for the black hole. So deriving this is what I'm going to do next. So there's a lot of thing happening here. So let me just outline, because I don't think I can do all this. So the matrix model is like this. I have a matrix with blocks. This is a black hole block. And then I have I call it environmental block. And then I have this link, like open string, right? So this is this big matrix, right? So I have a matrix model for this. So everything here is defined. I mean, defined interaction is defined. So first thing is that you want to find a background so that this one gives you some gauge theory, this one give you some gauge theory, and then you try to see what happened, right, with the link. So you can find that background. So this is certainly the background with a horizon. So you take XA equal to JA plus a gauge field, which I use B. B is the gauge field on the horizon. For dimension, so I put an R here just to keep the dimension. Otherwise, these are dimensionless, right? So just keep dimension so that B is of correct dimension. So you do that, and then you substitute in the matrix model, and then do the loose to large and limit, then you get a gauge theory for the horizon. Some horizon coupling, and then some integration measure on the fuzzy sphere, and then there's a R square, which is on the fuzzy sphere, R square, and then you have some. There's a d tau, yeah, and then blah blah blah, something like that. Okay, so there's a gauge theory like that. That's it. So basically, this BA, we have A equal 1, 2, 3. We have 3 of them. So it reduced to a set of B gauge field on the fuzzy sphere and a horizon scalar. So this will involve the scalar also, magnetic field and scalar. Yeah, but this is an indication the kind of theory you will get. Okay, so this gx square, 1 over gx square, is basically some L Planck and then some constant. There's no n. Okay, so just keep in mind of that. There's an important question about what's the choice of tau here, right? The tau here has to be chosen, which is correspond to this FIDO frame time. So this FIDO frame time here is basically defined by this relation. Yeah. At the stretch horizon, right? And then the t. Right, so there's a factor here which depends on the location of the stretch horizon, which you take like a Planck length above the Schwarzschild radius. So F is 1 minus R over R. Yeah. So you work it out at a proper distance of L Planck, right? This F factor, in fact, is including the square root, is n. So I have to do this choice of n, keep it so that to arrive at this, right? Because I want to describe everything in the FIDO frame. This is important. So, but this is not easy to see from the beginning. But now I explain to you. Okay. Okay, you do the same thing for this environmental block using the same FIDO frame time, because I want to eventually do the physics in the same time frame, right? So like what I do, derive the boundary condition. I transfer everything in this case in the same FIDO frame. So here you get a Maxwell theory. You can get a Maxwell theory. Not difficult. I mean, like that. So the picture here is that you now have a horizon, fuzzy sphere horizon, and then here you have some gauge theory, BA, and then in the environment here, you have some A, right? A, some gauge field, and then what about the fermion? The fermion is the important part, right? The fermion. On this horizon, you have fermion, psi. So what's the psi? So let's talk about the psi. This is very important, very interesting. In the last slide, we talked about the fermion, U and D, right? U and D dagger. They actually have a huge degeneracy. They can only either at energy 0 or go up to 1 step with energy like m pen over n, something like that. Either here or here. and there are 2n squared of them together. That's how you create this degeneracy. You put half of them here, half of them sit here, then that's a half Fermi C, which I was talking about, right? So one question you may ask is, okay, the picture actually is quite similar to Lenny Susskind talked about many years ago. He has a model of partons. So in his model of parton, he imagined the horizon is divided into Planck-size cell with area of L Planck square. And then let's say there are n square of them, n square of this cell. So each of the cell has a Hilbert space of dimension 2, either up or down, spin up or spin down. Right? So the total ground state degeneracy is 2 to the power n square, something like that. And so when you take the log, so you get an n square, and then get identified with a over 4g, right? So the model I talk about actually is basically reproducing this picture with the U and D being like the parton you put there, and you can either fill it or not fill it. That's the dimension 2. The question is now, okay, the question for that model is, why are these partons not moving at all? For example, what are they? I mean, why are they stuck? If they're moving, why don't they give you extra interaction? And what are they, right? So in my model, this question has to be answered. Are these moving or just got stuck? If they got stuck, why are they stuck? The answer is very interesting. It turns out these fermions, which are in the fundamental representation of the SU2, they correspond to the lowest Landau level. So if I start from my fermion has 2 indices and a alpha. These indices are not important, so let's forget about them for the moment. So the favor indices and the speed indices are not important in the moment. This alpha basically gives you the 2 species, right? This I is just giving n copy. So let's forget about that. So I basically have a column, right? This column. Now this column, I can construct a state. Construct a state m from minus j to j, and then construct the wave function with a coherent state. So I get some wave function, right, which is psi m. Now this wave function actually is explicit. I mean, because you know the coherent state, and these are just angular momentum basis. So this basis function well construct in terms of some d function, not d function. So it can be construct. So if you write this in terms of what do you call stereographic coordinate? Yeah, instead of angle, theta and phi, using stereographic coordinate on the sphere, then you find that actually this is of this form. Something like that. So this is a polynomial with degree up less than degree of polynomial of z with degree less than or equal to n minus 1. So in terms of coefficient, we have an n coefficient here, right? So these are like the orbital. So they satisfy a holomorphic, covariant holomorphic equation with a connection. The connection is precisely the monopole. So precisely the monopole. So that's the monopole which I constructed earlier, the Berry monopole, precisely. So the picture is that this equation, of course, can be obtained from the equation of the matrix model as a zero-mode equation. The equation I have, we have a d part also, right? But let's say consider a time-independent solution. That is basically this Kairos equation. So the Fermi C which I construct actually correspond to this lowest Landau level, right? In principle, you have a Berry B field. Let's say you have a B field on a sphere, on a plane, doesn't matter. You create a lot of Landau level, right? A lot of Landau level. One of them, the lowest one, is the lowest Landau level. Now, in this model, because of the special construction, this side comes from the fundamental fermion. If you start from some matrices, then you can also populate the other one. But this one only sit here. So they always sit at the lowest Landau level. Either you populate or not, right? So that's the picture. So that explains why you have the parton picture. So I will now call this a parton. These are basically some small loop moving on the horizon with some y. So what's a delta A, right? So I have n square of this Landau level, and then the total area is 4 pi r square. So it's something like L Planck square. So this loop are Planck size. Okay. Are there any questions? Okay. So yeah. So okay. So if this is the only thing, then it's still quite static, right? But once you decided to put a tangential E field, right? You put a E field. What happened? Now this loop, this Landau level can move. This is the guiding center movement, like a collective movement of this Landau orbit. Oh, so the lowest Landau level Lagrangian, will move. So this location was specified by some omega, become a function of time, right? So this is the Berry gauge field. These are the angle, right? So you have this Lagrange, this part. It can be derived from the model. So you have this one, and then if you also put a E field, right? Put a B field, then you can couple like this. So this is the this decide the motion of the Landau level in the presence of a external field. So the equation of motion from this is FAB minus this B can also generate F, right? So that's a QFAB, and then the Y is the physical distance, right? So this is an angle, and then there's some physical distance. So I call this. So it gives you something like this. So this is just Lorentz. Like usual Lorentz. You have a Lorentz interaction of a particle, well-line interaction, exactly like that. Nothing more, right? So this is the external potential. So in the limit, this Berry field is actually quite big. This F is okay. F is J, right? I talk about F is J, and J is N, and this is large, right? So compared with this is large. So you have a hot drift, basically. So this F, this Berry phase, actually this monopole is in mathematics. It's just a symmetric structure on the sphere, right? It just this symmetric structure actually enter into this equation for the fermion. So get a physical meaning as a Landau level. So you get equation like this for the velocity of this parton. So the current JB will be some density of the partons, and then times Q, and then times the drift, right? So you have some rho, and then Q square, and then F inverse, and then electric field. Now, basically, now it's clear because you have the two type of partons. Actually, they have negative opposite charge. So that will give opposite contribution here. Other than that, this F is antisymmetric. So you get an epsilon here, right? Epsilon here, and then the rest is just some number. The number will depend on the difference of the road density of U and D, right? So you work out all the factor of, and then you get n q square over 2 pi, and then nu of U minus nu of D, and then epsilon BC EC. So this is you get a Hall conductivity. So it's very much like the usual expression for Hall system, right? This n come from the n favor, and then this nu are the filling fraction. So nu U is the R we have over n square. The nu D is S over n square. So you get a Hall conductance, right? So the picture now is that we have this block, black hole, and the environment. Here I have this current, which is a function of the B, the volume gauge field. And environment, I have another set of gauge field, this A, right? To make a statement of the membrane statement, somehow I'm missing one thing, which is this gauge field has nothing to do with this so far. So if they have nothing to do with this, are independent. I mean, this is just independent system. It's happily living here with Hall, but the external world cannot probe it, cannot see it. So we need some mechanism to relate them together. And like open string. Now, this is open string condensation here. There's an open string condensation here. So that's so basically the idea is that you have this W here. So very roughly the idea, because I don't think it's justified to do the math here. But you can see the idea. The W is a when we divide the block, right? We have this block which is n by n. N is finite, big and finite. This block is n prime and n prime, which we really think is infinite. Okay, so n prime is the regularization. So you really divide the big symmetry into some smaller symmetry now, right? And the W is a bifundamental. So if you look at the covariant derivative, then you have some A mu WA. This A is from here, right? And then minus WA B mu bifundamental, something like that. So all these are U1 gauge field. So this is basically something like A mu minus B mu WA. So if we look at a vacuum configuration, so the kinetic term give you a term. The kinetic term give you a term like a potential. Like a potential. So if this thing condense, and not just condense, but if this is huge, we mean this, it costs a lot of energy, and then it will lock these two gauge field, and then supply the relationship between the two blocks, and then complete the relation of the membrane relation. Now, why is this condensed? So we have to look at the interaction of the length itself. Right? So in the matrix model, you have the commutator. Some of the commutator will have only W. Right? Some of the commutator is here. You have some mixed commutator, but some of the commutator are self-interaction. So there will be self-interaction for the length. So right? So the V, you have some V of W coming from some W delta W minus something like that, right? There are lots of this kind of term. So there will be some term with 2W, there's some term with 4W. Okay, so against the hex mechanism. So this term turns out you can have we have to find it's a big matrix. These are rectangular matrix, right? We have to find the configuration which make it condensed. So we make an answer, which then we find it. So there's a condensation. The W basically is like order n here. And then you plug back all the coefficient, and this will generate a potential for the gauge field of order n cubed. This is the, so when we say this is big compared to something, then it will log. What does it compare to? So what it compared to is to compare to, for example, the kinetic term of this field, right? So you have F square, and so these are kinetic energy. So you have to compare the kinetic energy of this with this, right? So in the end, and some of this has a radius, right? So some of this has radius r square. So in the end, after you go through the computation carefully, then you see that this is n cubed. All the other term, like kinetic term, they are at most n square order. So this is really much bigger. So you provide a locking of the gauge field. Actually, it's the tangential component. Okay, tangential component. So and so the final membrane statement is still this, right? You can still say is still this 1/4 pi JA equal to 1/4 pi F A N. But the current now here has a ohmic plus a Hall component. Okay, you may ask, where does it come from? I mean, I cannot just take it from general relativity. If I have a membrane model with the parton degree of freedom, it should come from there, right? So I should derive this for my parton Landau level system also. So that can be done. Oh, I just erased some of the thing. So this equation here, okay. That was the equation if I only have the Landau, if I only apply electric field to the Landau level, that is the equation. So the equation before was like this, F A B, and then Y dot, right? Some Q E A, something like that. Yeah, okay, yeah. So of course, this cannot have any dissipative effect if I only have this Hall system not dissipative. But remember our horizon. Okay, so not remember, but the horizon itself actually has been postulated to have a temperature. Okay, suppose you have a temperature not equal to 0, then this thing is actually the parton should be moving in the thermal background of the other parton, and then there will be collision, and then you have to take into account of that energy loss. So there will be some friction term. So some friction term, some eta, and then some y dot, some velocity, right? Friction. So assuming you have this term, and then assuming you have this term, and then this term is really coming from a thermal origin, then you do an estimate, right? I think T square. Yeah. So it's a power loss per unit time. So the energy loss per collision is about T, and the collision time is also of the order 1/T. So that's how we get like T square, right? So you can do a Kubo computation, which we haven't done, but it's quite robust, I think, this argument. So then you can generate, in principle, you can generate this. The 4 pi, I think you have to really do the Kubo computation, which I don't have at the moment. But anyway, so this is the picture of the current. So if you have this modified relation, then the relation, so you define U equal to R minus T minus R star, and V equal to T plus R star. So this relation is modified. Right, with some reflexive coefficient determined in terms of this guy here, right? And you can diagonalize this. I mean, this is basically just a 1/4 pi and then sigma 1/4 pi. So you can diagonalize this into diagonal polarization. Those are just left-handed, right-handed polarization. So if you have left-handed or right-handed polarization, hitting the black hole, you basically see a plus or minus of that effect, Hall effect. So the reflexive coefficient, in that case, plus or minus polarization, something like that. I don't remember off my head, something like that. So the D is D plus minus is this. Let me call this sigma xx, right? Sigma xx plus or minus sigma h omega. So you get a particular kind of a frequency dependent and chiral response for the resistivity. In the literature, people talk about this kind of thing as a phenomenological model. But people also try to find it in LIGO. I didn't know that. Once I do this, I check, and then wow, there's a big activity. But people cannot really make conclusion because when people make phenomenological template, yeah, there's a huge uncertainty, model uncertainty. But here there's a definite model, so maybe we have better luck. We can check maybe. What can I say? To submit model yesterday, I think we can actually talk, instead of talking about the entanglement between this bit and this bit, the cap, right? We can talk about the whole horizon and talk about what the inside and outside. I mean, the same computation, I think. The model is here. So instead of, here I only have 2 blocks, but I can add another block, interior block, invisible. Right? Interior, exterior, and then the black hole. So this thing also link, right? There's some free body interaction. So so I think that's an interesting problem to think about. In general, I think I'm quite happy with this. I'm quite excited about this model. A lot of things seem to, at least you can talk about them without guessing. There's a definitely microscopic model here. Even as a toy model, I think it's quite interesting. Okay, that's what I want to talk about. Thank you.
So you need an extra electromagnetic fields to see this modified dispersion relation. Right?
No, you don't need. But this is like the response. I mean, the field is just a. I mean, we're talking about this response function here. The electric field creates this response. The current, the response, yeah. So you don't need the electric field, but you Okay, maybe you need, as an experimentalist, you need to send in something to probe. Yeah. Okay.
Okay, so you can stay around for more questions for Chong-Sun or discuss among yourselves. And otherwise, yeah, you're free. Tomorrow, hopefully, 99% of the chance we should be able to have the regular workshop in person, according to the forecast, with the 1% possibility that suddenly the typhoon starts to accelerate. We will offer WebEx links at the web page, and I think you will also get emails tonight. And the government will announce whether there will be school at 8 p.m. tonight. So if you don't receive anything, it will not be closed. Well, at least I cannot tell you to come. Otherwise, I'm violating the law. If you come, it's your own, at your own risk, and it's your freedom. Yes. So yeah, let me know if you have any question. Feel free to, yeah, tell me. So otherwise, I'll see you tomorrow morning. Thank you.